on my laptop, so if you miss a class, you can actually, at the very least, listen to the lecture, and if there was a PowerPoint presentation, watch the PowerPoint presentation. For the past 3 years, I've been trying to figure out the best way to do this. In other words, the best way to get the lectures to the students. The files are big, so it's tough to find a place to host them. Like, the university doesn't give professors 5 gig of web space to store, a whole semester's worth of podcasts on. So I can't host them on my school account. Last semester I set up a web server in my basement that I ran myself, and students would just type in a URL that took them to my house and they could download the files there. That worked fine for a while until the constant requests on the wireless router started taking down the network in my house like 5 times a day, and I would have to restart the router. So that wasn't working very well. This semester I'm actually going to take all the recordings and upload them to YouTube every day. Because if you request what's called a director's account at YouTube, you can have unlimited uploads and unlimited size files. So I've done it with one file already, and it seems to work. So I think somewhere in the syllabus there's a URL, maybe the last page. Yeah. The very last page of the syllabus has my stuff, my office hours and whatnot. But at the very bottom, youtube.com/profile user equals Dr. Dave. I think if you go do a search for Dr. Dave, all one word, that will be the first hit that comes up. So bookmark that if you miss a class, as long as the system continues to work. And the upload process doesn't become too cumbersome, or as I don't find some other way to get this done, that'll be the place to find the lectures. It's been a pretty it's been a pretty nice way to eliminate the excuse of, oh, I missed that class, so I didn't learn that stuff. There's no longer any excuse for not hearing all the lectures. The other stuff on this page, my phone number, my office, which I almost never am there to answer, my email address, which is the best way to get a hold of me any time of the day from 5 a.m. till midnight. I seldom go more than a half an hour without checking my email. My cell phone number is there for emergencies, and it's particularly important for you guys having a relatively early class. I live up in Orange County, New York, like up in the Hudson Valley. So sometimes there'll be like an inch of snow here and 8 inches of snow up where I am, and it makes it very difficult for me to get to the train station to get into work. If you guys are here and 10:15, 10:20 rolls around and I'm not here, feel free to whip out the syllabus and have somebody call my cell phone to see if I'm, stranded on a railroad track somewhere up in upstate New York. I will try to do the opposite and call the office if I can, but that's really the only reason the cell phone is there, is for emergencies. My office hours are Monday, Tuesday, Wednesday. Monday, Tuesday at noon, Wednesday in the morning. And I'm usually almost always puttering around the science lab over here before class. Monday, Tuesday, and Wednesday also. And you can always sort of look for me around the science lab during the day. Thursday, I'm only around every now and then because I don't have classes on Thursday. But if you want to make an appointment to meet with me, I'm often here on Thursday. Just it's not a regular time. This class, Contemporary Physics, is about the 3rd time I've taught this class. And it's part of sort of a 2-semester sequence in physics in the Lang STS program. The first one is called Foundations of Physics. And the second one used to be called Modern Physics. Now it's called Contemporary Physics. I would like to call it Modern Physics, but they won't let me call it Modern Physics because there used to be a class called Modern Physics, and it's a different class, and you can't have people. You can't have 2 classes within like the past 12 years that have the exact same name but are different classes. Foundations of Physics covers motion and heat. And it is really physics from 1600 to about 1850. And it's a fairly historical approach to this subject. I mean, we start out reading Aristotle, and then we read Galileo, and we read Newton, and the course tends to be only sort of semi-mathematical, and really focused on the history of the sort of ideas in basic physics. Contemporary physics traditionally has talked about relativity and quantum mechanics, and a little bit of particle physics at the very, very end. which is physics from, say, 1900 to now. There's a lot of stuff left out in the middle here, and maybe we'll talk about it a little more. A gap in the material. Things like optics, electricity and magnetism, acoustics don't get talked about much. What I've noticed the past couple times I've taught contemporary physics is there's never really enough time to talk about, honest to goodness, contemporary physics. The lie that physicists are telling when they name their course modern physics is that modern physics is really 1930s physics. It's the beginning of quantum mechanics. It's the stuff that guys were doing in the 30s and 40s. And a modern physics course typically talks very little about the things that were discovered in physics from, say, 1970 to 2000, and the stuff that's still being discovered today. So the end of it winds up getting pretty squeezed, and I'm never sort of happy with how little I'm able to talk about the stuff at the end. So what I'm doing next year, and I didn't want to do it all at once, so this is sort of a transition, is I'm splitting this in half. And there's going to be a course called Space, Time, and Einstein. It's going to be a 3,000 level course. And there's going to be a course called Quantum Universe. That's going to cover just this stuff. And that's going to be 2,000. In order to make sure that there are some people around who can actually take the space-time and Einstein class, I decided that what I wanted to do this semester in contemporary physics is cut the relativity back from half the course to just like the first 5 or 6 weeks. So we're going to talk about Einstein for about 5 weeks in the theory of relativity, and still get a lot done, and still learn an awful lot about relativity. The reason for that is that, should you be terribly, terribly interested in this, next fall, you guys can take this. In other words, it's still going to be Einstein and relativity, but it's going to be in much, much greater depth. And so, yes, some of the stuff will be repeats for you, but it's going to be more mathematical, more technical, more equations, more problem solving, and it's going to be an honest-to-goodness science course in relativity. The quantum universe course, you can't take this, because too much of it would be a repeat of what we're going to do this semester. So the reason for cutting back on the relativity in this class, just a little bit, is so that, A, there'll be some people who might be interested in taking space-time and Einstein next semester, and 2, so we can get to this stuff, the good stuff, at the end. So that's the plan. And if you look at the, I guess the second page of the syllabus probably, there is a tentative schedule of topics. And you see that Einstein, that we'll have an exam on the Einstein on lecture 12. So that's only about 5 weeks. I mean, that lecture doesn't count. This lecture doesn't really count because it's just introduction. So really only about 5 weeks of stuff on Einstein. Then there'll be a unit on quantum mechanics. And this is what the physics courses tend to call modern physics. The basic introductions of quantum theory that happened in the late 20s, the 30s, the early 1940s. And then at the end, we should have a good 4 weeks to talk about honest-to-goodness contemporary physics. In other words, the stuff that physicists are doing right now. The second exam will cover only the quantum mechanics stuff. That's around lecture 22. And I thought I had dates. There might be dates for these on the next page. And then rather than having a final exam, there will be a final paper that's going to be asking you guys to do some research on a new machine being built in Europe called the Large Hadron Collider, which is being designed to answer some of the questions about particle physics that are still unanswered. So hopefully after talking about the stuff we're doing in lectures 23 through 28, you'll have enough ammunition to read up on this machine and understand something about what it does, or what it's trying to do. So that's a general list of what we hope to do. The grading is pretty simple. The next page, there's a breakdown of the points. I do a straightforward point system. Big things are worth 100 points, medium things are worth 50 points, and little things are worth 10 points. So there'll be two biggish exams that are worth 100 points each. The final paper is worth 100 points. The reading journal I'll talk about in just a minute. That's worth 100 points altogether. And every once in a while I'll give you a little reading, read this for homework and write a page on it, or I'll give you a short problem set to do, solve these two problems, or some short thing that takes you 2 or 3 days to do and is only 1 or 2 pages. Those things will be about 10 points each. And then there's 50 points reserved at the end for do you come to class every day, class participation, do you turn your work in on time, are you late frequently, and those sort of points are just sort of thrown in there at the end. But the bulk of your exam, bulk of your grade is the 2 exams and the 1 big paper. Is more than half your grade. The next couple pages I won't talk too much about. They're the official policies on academic honesty and attendance that they make you put in these syllabi. The official attendance policy is at, and it's actually changing. I don't know if you guys know this. The official policy is changing, I think, probably within the next year or two, from after 3 absences you can fail to after 3 absences your grade will be reduced by 1 letter grade, and then after 4 absences you can fail. Regardless, more than 3 or 4 absences and it starts to become an issue for official university policy, and it can adversely affect your grade. The other thing is just not coming to lectures. Recordings on YouTube notwithstanding will greatly hurt your ability to pass the class and pass the exams. The only people who get below a C in my class are the people who don't come every day. You have to work really hard to fail this class, but if you don't come to class, you will fail the class. So that's the unofficial policy. Again, official policy on lateness, official statement on plagiarism. The only thing I'll say about plagiarism is this: anytime you go anywhere outside of your own head for information, a good rule of thumb is to put a citation down. I routinely will pick the best sounding, most well-written sentence out of your paper and put it into quotes and put it into Google, and if I find it there, you get a big fat 0 on the assignment, and I have to do that. I do that probably more times than you'd think. Just a couple semesters ago, I took a particularly well-crafted sentence and put it into Google and found 75% of that person's paper in Wikipedia. Just copy, paste. So do not copy and paste. If you find something that's so brilliantly written that you simply must have it in your paper, put quotes around it and put a citation after it, and that's just fine. But if you copy and paste stuff, it will catch up with you, because I enjoy checking on that stuff quite a bit. The last page is just a little bit about sources and citations in general, the not copying and pasting stuff, and also just being aware of what you're using as your sources. Especially nowadays, it's becoming more and more common to use Wikipedia as like the main source for everything you write. And I'm guilty of that too. If I have to do a lecture on something I don't know about, the first place I go is Wikipedia, because it's a very good starting point for information. Everything is there, but it's only a little bit of everything. Some of the stuff you get from Wikipedia is very shallow. Some of the stuff you get from Wikipedia is wrong, or at least misleading, or very, very poorly written. So encyclopedic sources like Wikipedia and How Stuff Works are great starting places, but for any big papers, like the final paper that we're going to have for the class, you want to cast your research net a little bit wider. Focus on websites that have a .edu after them, so you know that someone at some university had something to do with them. And again, make sure you always cite those sources. Okay, so that's all I need to say about the syllabus, I think. Let me pass out the reading list. There are 2 texts for the class. I tend to stay away from sort of traditional hardback $100 textbooks for a bunch of reasons. One is with just the fact that I kind of have a problem with $100 textbooks on principle, and the way the textbook industry conducts itself. But the other is I teach such weird courses, it's kind of hard to find a textbook that covers everything in this class. or in any of my classes, really. So the two books for this class are one book on relativity called Simply Einstein by Richard Wolfson, who I actually met at the American Physics Society conference that I went to last year. It's a very well-written book, a very readable book, and the analogies are very, very good, which I can't say about all the books that you read about relativity. A book like Brian Greene's Elegant Universe, which I used to use as an alternate text for this course, I hate his analogies. I'm not crazy about his writing. I know he's a bestseller and his books are very popular, but I do not like them. This book I actually find very readable, and I think it does a very good job. So that's the book for the first half of the course. The second book, I'm not as happy with. It's really hard to find a book that does both quantum mechanics really well, like the historical stuff, and the really contemporary stuff. This does a really good job on the contemporary stuff, especially the stuff from like the 1970s and 1980s, when particle physics really started to explode. It does less of a good job with the history of quantum mechanics, like the stuff from the 30s and 40s, so I'll be probably supplementing a lot of that with other readings that I'll give you from the web and from a couple places, primary sources, things like that. But this book is called The Theory of Almost Everything, which is about the standard model of modern particle physics. And again, it's pretty well written, and the stuff that it does well. There's just some holes in it that I wish were filled. So we will not get to this book until after midterm. I do not use, or starting this semester, I do not use Barnes & Noble anymore as the textbook supplier, because last semester I had a very, very bad time with them not having all the books I requested, even though I always ask for a few extra. Like if the class has got an enrollment of 20, I always ask for 22, and they're always 5 books short. So this semester I'm using Blue Stockings. Has anybody had a professor use this bookstore before? They're on the Lower East Side. They're an independent bookstore, and they work a lot more closely with the professor. And supposedly they will like just come to our class with a big stack of books, and you can pay them with your credit card or cash. And get the books there. So I'm actually going to call them today and confirm that they will be here on the second day of class on Wednesday for people to buy their books. But try to get the books this week, either on Wednesday if they come, or before next Monday. You can head down to the bookstore and pick them up. They're cheap. Like one of them's, or if you want to order them from Amazon and pay a couple extra to get them shipped fast, they're like $12 and $16. So it's not. That's the other thing I like, is if I can keep the books under $50 for a course, I really try to do that. This thing I just passed around is a list of readings that will not change for the whole semester, so every week you should know what you should be reading in the 2 books. It's quite a bit of reading, especially in the Simply Einstein. Because we kind of contracted the relativity to the first 5 weeks, that means we'll be reading about 3 chapters in this book a week. But trust me, it's a really readable book, and 3 chapters a week should not be too hard. So that's for the first, 6 weeks of the class. What I want people to do, and the flip side of this, where it's a semester reading journal, is every chapter you read in any textbook, to just write a quick 1-page summary of the chapter. And that 1-page summary should do a few things. Just a quick, 1-paragraph summary of what the chapter was about. The next part is more important, which is making connections to what we've talked about in class. Sometimes the readings will be a little ahead of class, sometimes will be a little behind class, but you should always be able to relate something being said in the book to something that we talked about in class. If the book uses any terms that you don't understand, go into Wikipedia or wherever you have to go and define those terms and look them up. But most importantly also is raising questions. If there's something that you don't understand in the reading, to write down a list of questions of things that you would like to have clarification on. Things maybe completely off-the-wall tangents that the chapter makes you think about. It's easy to get dragged off into off-the-wall tangents when talking about relativity, and so that will happen a lot. So every week you should be writing at least 3 pages. For the first 6 weeks, you should be writing 3 pages, 3 1-page chapter summaries, and then the reading slows down a little bit after midterm. I'll be collecting these. There are 3 due dates listed here. Wednesday, February 28th. That pile is worth 50 points. The other 2 are worth 25 points, just because there'll be more there'll be 15 chapters in the one I collect on the 28th, and only 6 in the ones I collect in April and May. So keep up with this, both because I want people, I mean, if the reading journal says, you know, by Monday, February 12th, you should have read chapters 7, 8, and 9 in Simply Einstein, because I want to know if I mention something that was mentioned in the book that everybody is on the same page and has read that. But also, if you put off writing these chapter summaries and have to write 8 of them the day before it's due, it's just not going to happen. So trying to stay up to date on that. And again, that is the sort of major weekly assignment. Any readings? No, they're not going to change. This is a pretty set in stone reading list, so you can count on that. I will try to put this online somewhere also if you lose it. I tend not to use Blackboard very much just because I find it kind of clunky and it just, I don't know. I'm not a big fan of that kind of web interface. Usually, if I need web stuff for a class, I'll just write my own web page in HTML. Like I've always done. But I might put a few things like the syllabus, like this reading list, up on Blackboard just so people know that they're there if they lose track of these papers. Okay? Any questions about what? I mean, I'm going to talk a little bit more about what we're going to cover this semester. But any questions about procedural things about the class? Okay? Let me check the roster really quick and make sure people who are supposed to be here are here, and see if there's anybody trying to add, because I think there are actually a little bit of room opened up. Eve Alexander, Sasha Bush, Leslie David, David Eisenhower's here, Aaron Gallagher, Thomas Colstrud, Shayna Levine, Claire's here, Sienna is here, Miki Oshima, Cassandra is here, Carolina Quiros, Carolina, right? Yes. Oh, Carolina. Cameron Saul, Miles, there you are, Lauren Tully, Zachary Warsavage, Zach, and Calla Wright. Yeah. Okay. Anybody I didn't call? I got you. Anybody I didn't call who's looking to add? No. Good. Oh, wow. Well, if that's all it is, it's going to be a very nice sized class. Let me start. How do I want to start? I want to start, I guess, recapping this sort of division of subject matter, and that'll get us into talking about talking about some of the basic physics we need to know, even to understand the terms that are being tossed around. One of the decisions I made when developing these two classes is not to make foundations of physics a prerequisite for contemporary physics. The logical thing to do would be to make foundations a prerequisite, so you have to take foundations before you can take contemporary physics. The problem with that is here at Lang, where there are no sort of science requirements, there's not a whole lot of incentive for people to take 2 or 3 science classes. And because contemporary physics is so much more interesting than foundations of physics, it would have a much well, I mean, it has a much better chance of drawing more students if you don't have this prerequisite in here. It's not a problem, except that there's some vocabulary that a lot of you are going to come out into this class missing compared to the people who have foundations of physics, which is actually great. Is anybody here in foundations?
Well, I did.
You had physics somewhere else, and you guys were in foundations. So there's some vocabulary, things like velocity and acceleration and force and energy, that we really need to understand what these terms are if we're going to understand how they're used in modern physics. Because what makes modern physics so interesting, let's take relativity. What makes relativity so interesting is the departure that it represents from classical physics. And if you don't understand the terms of classical physics, it's hard to really understand how relativity is a departure from that. So the first piece of physics we talk about in the Foundations of Physics class is a branch of physics called mechanics, which is basically how and why do things move. The mechanics owes almost everything to Galileo and Newton. So we're talking about, say, 1600 for Galileo, to Newton's Principia was published in 1687. So 17th century physics. So defining terms like velocity, acceleration, and force. And we'll talk a little bit about that. The next thing we talked about in Foundations of Physics is thermodynamics. Thermodynamics is the study of heat and energy. It's not as simple as mechanics in that the development of thermodynamics involved dozens and dozens of scientists. But we're talking about a time period from, say, 1750 to 1850. People started figuring out how. Well, people started working on chemistry and studying, figuring out that things are made out of atoms. Say, motions of atoms. And eventually figured out that what heat was just atoms moving around. And so this discovery that motion when applied to the little atoms that make things up is what we think of as being heat. We will need very little of this semester, except to understand in some detail this word, energy. So that's the piece of that we will need in this class. Somewhere in between here, I'm going to put relativity here, which we associate with Albert Einstein. And his big year in relativity was 1905. We just celebrated the 100th anniversary, year before last, of Einstein's miracle year, where he published 5 scientific papers which revolutionized physics and pretty much invented a whole new kind of relativity and laid the groundwork for quantum mechanics, and once and for all confirmed the existence of atoms. So Einstein, in 1905, closed out one chapter in the history of physics and opened up a brand new one. Relativity is about motion. It's about the motion of things, as the name suggests, relative to one another. But where this class differs from a lot of, and even more so, I think, the space-time and Einstein class, but where I try to make this class different from a lot of modern physics classes is I don't want to just sort of pull the ideas of relativity out of thin air, as if they just came out of Einstein's brain because Einstein was a genius and he thought up all these crazy ideas. Relativity came from solving some problems in physics that existed from, say, 1850 until 1900. And a lot of that has to do with electromagnetism. Electricity, magnetism, and light, which at first glance, don't really even seem to have anything to do with one another. It turns out that they do. And we'll talk about next Monday what they have to do with each other. And so there's a whole bunch of physics that usually occupies a whole one semester course. If you go to a sort of traditional physics department and take physics 1 and physics 2. Physics 1 is this, physics 2 is this, electricity and magnetism. And you learn about electric fields and magnetic fields, and you learn about electric currents, and you learn about light, and you learn about all this stuff that we really don't have time to spend the whole semester on here. And yet I want to talk just enough about this stuff so we see how these ideas lead Einstein to make some very surprising conclusions about the behavior of light and how that has to do with the motion of things relative to one another. The last bit we want to talk about this semester is quantum mechanics. Which we can think of, we can summarize quantum mechanics as they're the laws of physics that govern atoms and things smaller than atoms, so subatomic particles. Once we believe that atoms exist, and people had pretty much decided by the middle of the 1800s, yeah, these things called atoms are real. They're really there. They're not just some sort of made-up model for explaining what happens inside of stuff. They're honest-to-goodness things that everything is made out of. Well, once you believe that, the next order of business is to try to figure out what atoms do. How do they behave? What are the rules, for example? Say you're a chemist, and you know that when you put sodium and chlorine together, they make sodium chloride. You know, when you put carbon and oxygen together, they make carbon dioxide. You want to figure out what's going on there. What are the rules that govern the forces between the atoms? What holds carbon dioxide together into CO2? Why don't those C's and O's fly apart? So some of quantum mechanics grows out of an attempt to understand how atoms behave. The other thing that it grows out of, though, is an attempt to understand how light and matter interact. For example, if you heat something up enough, it gives off light, right? Inside of every one of the light bulbs in this room is a gas that's being heated up so much that it gives off light. If you take a regular light bulb and an incandescent light bulb with a metal filament, a tungsten filament inside, if you heat that light bulb up enough, it gives off light. And the question is, why? And where does the light come from? Was the light in there already, just waiting to be set free by some electricity? What determines how much light is given off? What the color of that light is? What the intensity of that light is? So what is the interaction between light and matter? And we'll say quantum mechanics is from 1905 to, when do we pretty much have it all figured out? Let's say 1950. And people really thought around 1905 that they had just about had it figured out. That Einstein had figured out relativity, Maxwell had figured out what light is. We can, pretty much this entire subject, we can attribute to James Clerk Maxwell. He's the big name in electricity, magnetism, and light. Maxwell figured out what light was. Einstein had figured out the speed of light and how light moves. And all that was left now was to figure out the forces between atoms. And Newton told us everything we need to know about force. And Galileo told us everything we need to know about motion, so if we can figure out the forces between atoms and how they move, we'll pretty much have all of physics wrapped up. Max Planck, who was one of the founders of quantum, one of the sort of big names in early quantum mechanics, was told by his graduate advisor not to bother getting a degree in physics, because in another 10 years, physics will all be figured out. All the questions will be answered, and there'll be no more new work to be done. Well, Max Planck did get a degree in physics, and he pretty much invented quantum mechanics and led to another 50 years of figuring out that the rules governing the motions of atoms and molecules and subatomic particles are much more complicated than the rules governing the behaviors of baseballs and cars and blocks rolling down ramps and the sort of silly problems that one does when studying what's called classical, and I'm going to divide this into two branches here. Classical and modern. So when a course catalog says modern physics, what they mean is relativity, quantum mechanics, up to about 1950. And they never get to the good stuff. And what I hope to do is to get to the good stuff here, which is the stuff that was discovered after the 40s and 50s. The fact that atoms have a nucleus with protons and neutrons. The fact that when you start banging into that nucleus, you make all sorts of particles, not just 3 or 4 particles, but hundreds, maybe 1,000 different kinds of subatomic particles. That there are forces in nature that are more complex and different from the force of gravity or the force of electrical traction that holds carbon and oxygen together as CO2. There are nuclear forces. There are particles that are responsible for carrying forces from one particle to another. The whole field of particle physics say 1960 now grows out of trying to investigate the behaviors of ordinary atoms. And what we find is that there's a lot of stuff going on in nature besides the ordinary atoms that make up everything in this room. There's all sorts of weird particles that exist in nature. And understanding the simple particles requires understanding the sort of weird exotic particles. So we'll try to spend the last 4 or 5 weeks of the class talking about honest-to-goodness 20th and 21st century physics. But today, I want to come back to this and just spend some time defining the terms that will be necessary to understand anything that Einstein is talking about, and just to make sure that we are all on the same page and have a basic understanding of a few concepts in physics that, while simple, it takes an awful lot of work in introductory physics class to make sure that people use all these terms properly. What Galileo's big achievement was in sort of practically single-handedly inventing physics as an honest-to-goodness science was the idea of precise measurement, was the idea that you could do an experiment and attach numbers to things and write equations to relate those numbers to one another, and come up with rules that describe something as simple as, if I roll a ball down a ramp, what happens? Well, it rolls down. Well, how fast does it roll down? Well, I don't know. Take measure how much time it takes to go from one end to the other. That'll tell me if it's going fast or slow. But, like, how fast? Like, the number. Assign a number to that. And is it always going to the same speed, or does it speed up or slow down? Well, if you think about it, when something's rolling down a ramp, it speeds up. Well, how much does it speed up? Does it speed up the same amount every second? The same amount every inch? Okay. Galileo was the first person to actually do experiments and associate numbers with all of these quantities. And this science of the study of motion involves only a very small number of things that one can measure about the universe. One of the first things that people measured about the world was distances, the distances between things. Distance is, or measurements of what we would call space, sort of a fundamental property of the universe. And we will talk a lot when we talk about Einstein about sort of what space is, or what it means to say that this thing and that thing are 10 meters apart. But distance is a fundamental quantity. You can't reduce distance to something else, as a combination of two other things. So I'm going to make a list here of fundamental quantities in units that we use to measure. The unit we will use to measure distance is the meter. Oh look, here's one. Meter, and 1 meter. Everybody should know how big a meter is. A meter is about a yard. This is a meter thick. It is a meter long. There are lots of other units we can use to measure distance. Inches, miles, light years. They're all just a unit of distance. And what a measurement of distance is a measurement of how far apart two things are in space. So space is a sort of fundamental quantity in the universe. The other fundamental quantity in the universe is time. We use seconds as our basic unit of time. There are other units of time, centuries, nanoseconds, days, years. Whatever you measure time in, you're measuring the distance between two things in some sense in time. And it's hard to really pin what that means down in any sort of reasonable way. In other words, it's very hard to define the word time without using the words like before and after, which really I challenge you to define the words before and after without using the word time. Time is a tricky thing. And we'll talk a little bit about time when we talk about relativity, a lot more about time in the space-time and Einstein class, where we talk about time travel, we'll talk about things like that. We won't have a whole lot of time for that in this class. But time, again, is not reducible to something else. It's a fundamental quantity, so it gets its own unit. Another fundamental quantity is mass. Mass is a measure of how much stuff there is in something. It's almost the same as what we think of as weight. But weight is a function of how much gravity is pulling on that something. The difference between mass and weight is, if I took this cup of tea, okay, it has a certain weight, it's about a kilogram, okay, of mass. But the only reason it's heavy to pick it up is because the Earth's gravity is pulling it down. If I took it out in space and let it go, right, it wouldn't fall, it would just float there because it doesn't have any weight. But it still has mass. I would still have to exert a force on it to push it and pull it around. And the more massive something is, the harder it is to push it. In fact, one can make an argument that mass is not a fundamental quantity. Really, the fundamental quantity is force. But in the metric system, in the standard, what's called the SI system, the Système International, the International System of Measurements, which is what the metric system is called today. We consider mass to be fundamental. How many atoms worth of stuff is in a substance is a fundamental quantity. There aren't too many more than those. An argument can be made for temperature. The temperature is a fundamental quantity. But it's really not. You can reduce temperature to energy and define energy in terms of these other three things. So there's some questionable ones, like temperature. And we may, in the course of defining some more units, come up with some other ones. But distance, mass, and time will get us a very, very long way in this class. Because while these are the fundamental units of measurement that are not reducible to anything else, There are lots of other things we can measure that are combinations of those three units of measure. We talked about Galileo. Galileo was concerned with quantifying motion. That when I roll a ball down a plane, or when I drop a weight from the top of the Tower of Pisa, how fast does it move? Well, the quantity that we associate with the term how fast is what? We ask how fast is that car going? Okay, speed, or what a physicist sometimes calls velocity. Okay? Velocity is distance divided by time. So it's a combination of these quantities. How far did you go and how long did it take you to go there? So any distance measurement divided by any time measurement is always a velocity. If you're measuring the velocity of a car, it's how many miles does it go in an hour, and your unit is miles per hour. If you're measuring the velocity of a glacier, it might be how many centimeters does it go in a century, and your unit of velocity is centimeters per century. If you're measuring the velocity of a galaxy, it might be how many light years does it go in a decade. So your unit of velocity would be a distance measurement, light year, divided by a time measurement, a decade. We will always use meters per second. Meters per second is the traditional metric unit for time. I will occasionally, every once in a while, just to put things in terms that we're familiar with, talk about miles per hour, because we all have a pretty good grip of what 50 miles per hour or 100 miles per hour is. But the unit we'll be using is meters per second for the most part. So the equation for that would be velocity equals distance. One little quibble here that will only sneak up on us every now and then is that physicists actually mean something slightly different by speed and velocity. And it won't be very important to us very often, but it'll come up every now and then. Which is when a physicist says speed, he or she means just what your speedometer in your car measures, which is how fast you're going. When a physicist uses the term velocity, they also are including in that the direction that you're moving. A quantity that has direction is something that physicists call a vector. And in order to really deal mathematically with vectors, you need to know trigonometry, and you need a scientific calculator, and you need to poke around with sines and cosines a lot. And we're not going to do that, but what we need to know is that velocity is speed and direction. So that if you're going at the same speed but changing direction, your velocity is changing. Okay? So a change of velocity can either be a change in your speed or a change in your direction. That's important when we talk about force. Okay? And we'll get there in a minute. Now, physics would be very easy if everything always moved at the same speed. Unfortunately, things sometimes change speed. A change in speed in physics is called an acceleration. For example, if you have a car, and if you pick up a copy of Car and Driver or Road and Track or something and read the review of some new car, it'll tell you, its gas mileage, and it'll tell you all these stats about the car. And one of the things it will tell you is that it goes from 0 to 60 in 11.2 seconds. That is acceleration. It's how fast does it change its speed. It goes from 0 miles an hour to 60 miles an hour in 11 seconds. So it's a change in velocity. How much does its speed change, 0 to 60, and how long does it take to do it? So when something is changing its speed, it's accelerating. So the units for that are going to be the units for velocity divided by the units for time. In road and track, it would be miles per hour per second. In the metric system, it's going to be meters per second per second. And sometimes you can say it like that. When you drop something, for example, its acceleration is 9.8 meters per second per second. That's what Galileo discovered, dropping things and rolling things down ramps and so on. So every second that something is falling, it goes 9.8 meters per second faster than it was going the previous second. But a compact way to write that in physics is meters per second squared. Second per second. The equation for this is acceleration is a change in velocity over time. Now that's all Galileo did. Galileo spent pretty much his whole life precisely defining velocity and figuring out what it means for something to accelerate at a constant rate. He never addressed the question of why things accelerate or what makes something accelerate at a certain rate. That was left for Isaac Newton. Isaac Newton was the one who formalized this notion of the laws governing why things move and how things move. And Newton's contribution to physics can be summed up in three main laws of motion, which are called Newton's laws of motion, which are probably the most, really one of the few laws that I make students memorize sort of verbatim when I teach introductory physics. And they're all well known enough that you've probably heard the phrases involved in Newton's laws of motion, even if you don't associate them with Newton or really know what they mean in terms of physics. The first law is that an object at rest remains at rest, an object in motion remains in motion, unless they're acted on by some kind of force. And it seems like a very obvious thing to say, that an object at rest will remain at rest unless a force acts on it, that an object in motion will remain in motion unless a force acts on it. But it was by no means obvious before the 1600s, when people's belief in why things move was completely different, and based a lot on the teachings of Aristotle. I don't want to go in too much into Aristotle in this, because I start every class by picking on Aristotle. Almost every course I teach. But it's instructive to look at the alternative. I mean, what is the alternative to Newton's law? The alternative to Newton's law is this idea that objects, if left to their own devices, will move in the way that is natural to them. For example, if I pick up my keys, okay, and let them go, what will happen to them? Okay, they'll drop. Now, why do they drop? Okay, we would say due to gravity, right? And to us, what gravity means is it's some sort of force that acts on things. It's some sort of pull that pulls them to the ground. That's not what gravity meant to Aristotle. To Aristotle, gravity was a property of the keys. And the reason it has gravity is because of what it's made of. What are my keys made of? Metal. And where does metal come from? It comes from the earth, right? To Aristotle, what will we say the keys are made out of? If we believe in the four elements of the ancient Greeks, they're made of earth, right? So why do they move down towards the earth? Because they want to be where the earth is. In fact, that's why the earth is where the earth is. To Aristotle, earth and water want to be at the center of the universe. So anything made of earth or water, when I let it go, will naturally move on its own accord to its natural place. What about the moon? What does the moon do? It moves in a circle, right? It does not fall to earth and come crashing down. It follows a path through space that is a perfect circle, and it never speeds up, and of course it does really speed up and slow down, but according to Aristotle, it never speeds up and it never slows down, and it goes in a circle forever and ever and ever. Now, can the moon be made out of rock if Aristotle's theories are right? No. If the moon were made out of rock, it would come crashing down to the center of the universe where it belongs. So the moon must be made of some special material whose natural motion is to move in a circle. This material was called ether. And so the things in the heavens, the sun, the moon, the planets, the stars, that all revolve around the Earth once a day. And of course, we know that they don't really revolve around the Earth once a day, right? The Earth spins on its axis and makes it look like they're going around us. But they're made out of something other than rock, because their natural motion is to move in a circle. Nothing's pushing the moon in a circle. The moon is moving in a circle because it is natural for the moon to do so. This is what Galileo and Newton were up against in 2,000 years of this stuff. Newton says no. Things do not move because they have some natural inclination to do so. Things only move if they are pushed or pulled. So Newton's first law, the law of inertia, which we're going to come back to when we talk about relativity, that an object at rest will remain at rest unless an outside force acts on us, says that the only reason for these keys to fall is if some outside force pulls them down, and that's the force we call gravity. The only reason for something to stop moving, for example, if I take a book and I push it across the table, Aristotle would say, watch, okay, it stops. That's because it's natural for that book to be at rest, not moving. When you push it, you are making it behave unnaturally, and that unnatural motion will eventually wear off and the book will stop. Newton says no. When you push something, it's going to keep moving at the speed you pushed it until what happens? Until something makes it stop. What makes it stop in this case?
Friction.
Friction, right. The friction between the book and the table takes the energy away from the book and slows it down and makes it stop. So Newton says anytime something's changing speed, if it's speeding up, slowing down, or changing direction, that means there's a force acting. So a force is an interaction that causes an acceleration. And so that's Newton's first law, that things don't change their motion unless you exert a force on them. Newton's second law says how much a force you need to change something's motion. And that's related to that object's mass. The more massive an object is, the harder it is to change that thing's motion. The harder it is to speed it up, the harder it is to slow it down, the harder it is to change its direction. So, to Newton, and this we can summarize Newton's second law as an equation. Force equals mass times acceleration. Probably the second most well-known equation in physics, the first being E equals mc squared. So Newton's second law of motion says that if you've got something and you know its mass, and you know the force being exerted on it, you can tell how that object will accelerate, how its motion will change. The units, then, for acceleration are going to be the units for mass times the units for acceleration. The units for force are going to be the units for mass times the units for acceleration. So the unit for mass is the kilogram. The unit for acceleration is a meter per second squared. And so those are the units for force, which is a very cumbersome thing to write out every time you want to talk about a force. So we call this thing by a name. One Newton. So the metric unit for force is the Newton. It's not fundamental, but it has a new name. Newton's third law of motion, just to mention it, just for completeness, since we're talking about Newton. Newton's third law of motion is that can be summarized in sort of as few words as possible, as for every action there's an equal and opposite reaction, which is to say that a force is not something that an object has. A force is an interaction between two objects. And it's one of the hardest parts of introductory physics is to get people to let go of their colloquial usage of the word force. I mean, we use the word force in everyday language in a lot of different ways. His argument was more forceful, as if force was something that your argument had. We're sending a larger force to Iraq, as if force was something that a battalion of a military unit has. In physics, force is not something that you have. Force is something that happens between two things. So you cannot have a force with one object. If I have my keys, where do my keys go? If I have my keys, okay, the keys don't have a force. They feel a force between them and the earth. You need two objects to have a force. And the force between them is equal. A force is an interaction, which means that the keys exert a force on the earth that's just as big as the force that the earth exerts on the keys, which seems kind of crazy, but it's true. In other words, the earth pulls the keys down, the keys pull the earth up. And the earth, when I let the keys go, okay, actually moves a little bit towards the keys. Okay? If the earth and the keys were the same mass, they would move together say, instead of dropping my keys, say I dropped an earth. Okay? Here's an earth, earth 1, and here's another earth. Okay? And I pick this earth up and I hold it here and I let them go. What happens? Well, there's a force of gravity between them, and that causes them to move. And Newton's equation F equals ma tells you how much they accelerate. And because they have the same mass, they will accelerate the same amount, and they'll do this. Now, if I replace this with my keys, the situation is the same. There's a force between them. The force between them is identical. But if we use Newton's equation F equals ma on both of them to figure out how much will they accelerate, the force is the same. What's different is the mass. So this little mass has a big acceleration caused by this force. This big mass has a very tiny acceleration caused by that force. If we multiplied the mass of the keys times its acceleration, we would get the same number as if we multiplied the mass of the earth times its acceleration. Now the mass of the earth is 1, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 kilograms. So this acceleration is very tiny, right? It's going to be 0.1, 2, 3, 4, 5, 6, 7. It's nothing we could ever measure. But it's real. And Newton's third law, every action has an equal and opposite reaction, says the earth can't exert a force on the keys without the keys also exerting a force on the earth. And the forces are exactly the same size. The accelerations are very different because the masses of the objects are very different. But the forces are identical. That's Newton's third law of motion. We won't need that much this semester. We will need F equals ma just a little bit. And we'll need to know what a force is. So we should have the word in our vocabulary. Now, the other thing that Newton did is try to, well, he didn't do a very good job, but he tried to answer the question of why things fall to the earth. In other words, what is this thing that happens that causes things to fall to the earth? Why does the moon move around the earth in a circle? Why does the earth move around the sun in a circle? By this time, by 1687, most scientists had accepted the fact that the earth moves around the sun and not the other way around. But why? Why does the earth move in a circular or elliptical path around the sun? Why does the moon move around the earth? Why does Jupiter, who Galileo discovered, has 4 little moons that go around it? Why do those little moons move in a circle around Jupiter? Aristotle's crazy ideas aren't, right? It's not because they naturally love to move in circles. If you're moving in a circle, said Newton, your velocity is changing. Your speed might not be changing, but your direction is constantly changing. If you're moving in a circle, when you're here, you're moving that way. 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 So when you're moving in a circle, your velocity, the direction of your speed, is always changing. If that's true, there must be a force at work. There must be some force changing your velocity. And Newton said, well, which direction does that force have to be? Well, I'm not going to get into it too deeply. But if you think about how to make something move in a circle, I don't have any suitable toys in here. I always use my power strip. Okay, suppose I want to make my power strip move in a circle, right? If I just do this to it, it moves in a straight line. You know, Newton's law says if you just push something, if I drop it, it moves in a straight line. How do you make something move in a circle? Okay. One way I could do it is this, right? If I have a force that's always pulling on this thing, it will move in a circle. What direction does the force have to pull? It has to pull in the direction that the cord is going, right? A cord can't pull in any direction other than along the length of the cord. So when the thing is here, the cord is pulling it this way. When the thing is here, the cord is pulling it this way. When the thing is here, the cord is pulling it up. When the thing is here, the cord is pulling it like this. The force on this is always towards the center. So Newton said, in order for something to move in a circle, there needs to be a force always pulling it towards the center. Center, 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 center. And Newton looked around and said, look, the moon moves around the earth in a circle. Therefore, there must be a force between the earth and the moon. And it's not just a force on the moon, remember, since forces are interactions. It's a force between the earth and moon. The earth goes around the sun in a big circle. Therefore, there must be a force between the sun and the earth that pulls them together. Jupiter's little moons go around Jupiter in a circle. Therefore, there must be a force between Jupiter and Jupiter's moons. Any object I pick up and let go is pulled to the earth. Therefore, there must be a force between every object and the earth. Newton took all these observations and generalized them into a rule, which is that every object in the universe exerts a force on every other object in the universe, and that force is called gravity. Newton was the first person to connect physics here on the earth, the fact that when I let something go, it falls, with physics up there in the sky, the fact that the moon moves around the earth, Jupiter's moons move around Jupiter. All the planets that were known in Newton's time, Mercury, Venus, Earth, Mars, Jupiter, and Saturn, all move in circular paths around the sun. Why? Because of one force, and that force is gravity. So the other thing that Newton did, besides just explain how forces work, is identify one very important force, and that's the force of gravity. And he wrote an equation for it. And I'll give you this is maybe going a little further than I wanted to go today, but we'll go ahead and put that equation up on the board. He wrote an equation for it by simply figuring out, well, how hard would the Earth have to pull the moon to make it go, to keep it from flying off into space? In other words, the moon wants to follow Newton's first law of motion. It wants to continue moving in a straight line forever and ever and ever. But the Earth's gravity keeps pulling it back. Same thing with this thing on a string. If I were to ever let that go, it would go flying off in some direction that I last had it pointed. So Newton said, how big does this force have to be between the Earth and the moon? What's the size of that force? And he said, came up with a number. He said if you take any two masses, this can be the Earth and the Moon, Sun and the Earth and my keys, whatever the masses of those two things are, that are some distance apart, that there's a force between them that equals some number, which we'll talk about in a minute, times the mass of one times the mass of the other, divided by their distance squared, and that square is very important. We're going to come back to it at a later date. This is just a number. 2, 3, 4, 5, 6, 7, 8, 9, 10, 6, 6, 7. In metric units, it's equal to that. It's a very, very small number. This law of physics is called Newton's law of universal gravitation. Universal because it applies to every object in the universe. So the Earth exerts a force on the Moon exerts a force on the Earth, Sun and Earth exert forces, the Earth and Mars, Jupiter and Saturn exert forces on one another, Mars and you, there's a gravitational force pulling you towards Mars right now. There's a gravitational force between you and the person sitting next to you. Now, the reason that we all don't go flying together in a lump in the middle of the room is because this number is a very, very, very small number. How would you find the force of gravity between you and the person next to you? Well, you would take your mass, 60, 80 kilograms, times their mass, 50, 60, 80 kilograms, divided by the distance between you, about a meter. Right? So 80 times 80 divided by 1 meter squared. 1 meter squared is 1. That's about 160. Times, 1600, times this, 0.0000000000667. And the number you would get is like 0.0000001. Well, that force, while real and while there, is much, much smaller than the force of friction between your butt and the chair. And so you don't go sliding across the room and stick to the person next to you. But if you were to take us all out into space, far, outside of the solar system, and put us all in space in these exact, take the chairs and tables away, and just stick us in space in these positions, over the course of several weeks to several months, we would slowly, slowly drift together, and it would take a couple of months. I did the calculation once. Okay, drift together and clump together into a little pile of people, wherever the center of mass of the of our bodies is, somewhere around here. Okay. But that force is so small as to not be noticeable. But Newton said it's there. It has to be there. Because it's the simplest way to explain all these phenomena we see in nature. The fact that things fall, the fact that the planets move in circular orbits. And so it was really the first moment of something that physicists refer to as unification. And one way to look at this whole progress of physics that I put on the board a little while ago, from mechanics to thermodynamics to relativity to quantum mechanics and particle physics, is as a series of unifications, a series of taking two things that look to be completely different phenomena and explaining them in terms of one equation. For example, the fact that this pen falls to the table when I let it go, and the fact that the moon moves in a circle around the Earth seem like completely different things. And yet this equation of Newton says, no, those are the same thing. Those are a result of the force of gravity. The same force that causes this pen to fall is the force that holds the moon in orbit as it moves around the Earth. And no, we don't need a different physics to explain what happens here on Earth and what happens up there. To Aristotle, the physics of what happens on Earth and what happens up there were completely different. Things on Earth are made of rock and water, and their natural motion is down. Things in the heavens are made of special magical ether that never falls and never floats away and never runs out and shines by its own light and continually moves in circles forever and ever and ever. To Aristotle, the heavens and the earth were completely different realms governed by completely different laws. To Newton, they're the same. The force of gravity applies everywhere to everything. And we'll come back to this idea of unification, the idea that I don't have it up there anymore. In the 1800s, electricity, magnetism, light were thought to be completely different things. And they seem like completely different things, right? Electricity comes in positive and negative charges. It flows through wires. It somehow happens in the dryer when you put your socks and your sweater in there, and it makes things stick together. Magnetism happens when you dig certain kind of weird rocks out of the ground. They stick together, and you rub a compass needle on them and it points north. Light comes from things that are hot. Electricity doesn't come from things that are hot. You don't heat something up and it becomes electrical, but you heat something up and it gives off light. They seem to be very different phenomena. Maxwell showed that they're actually the same phenomena. Einstein, what he does in terms of his theory of relativity can be thought of as unifying our description of motion with our description of light, so that they make sense together. So we'll come back to this idea that what physics is trying to do is to explain the largest number of phenomena with the fewest number of equations, the fewest number of rules, the fewest number of quantities. And a lot of times you'll hear in the news today that physicists are looking for something called a unified theory, or a grand unified theory, or a super unified theory. And what we'll talk about the very last few weeks of class is the idea that all the phenomena of nature could be like this. In other words, we could take everything that happens with light, with atoms, with electrons, with protons and neutrons, with all the forces that happen in nature, and express them in terms of one simple set of equations. We're not there yet, but if you look at the progress of physics from Galileo and Newton's time until now, one way to look at it is as a series of these unifications, where somebody takes several phenomena and shows that they're just different aspects of a single phenomenon. So that's force, and all we'll need to know about force. On Wednesday, I'm going to do the same thing we did today with force, with the idea of energy. And we're going to talk about the idea of energy because it's very important in one of Einstein's most famous equations is the equation E equals mc squared. E stands for energy. So if we're going to understand what that equation means, we need to understand what energy means. So what I want you to do between now and Wednesday for homework is to, in preparation for talking about Einstein, is to write for me everything you know or think you know about Einstein, and the theory of relativity. Without consulting any outside sources. So, yes, it may be very short. But everybody thinks they know something about Einstein, right? I mean, the interesting thing about Albert Einstein is he's one of the few scientists who's crossed over from being just some science guy to sort of a pop culture figure, an icon of something. You cannot go to Barnes & Noble and buy a bookmark with a picture of James Clerk Maxwell on it, right? But you can go to Barnes & Noble and buy a bookmark with a picture of Albert Einstein on it. Why is that? I mean, what is it about Einstein that, there's something that he's become the iconic image of scientists. But everybody also, I think, probably thinks they know something about relativity, or at least what it's about. What is the theory of relativity about? What are some of the things it says? So if you can do that, this should probably be about a page, maybe as many as 2 pages if you think you know more than that. But anything from biographical information about Albert Einstein, where was he from, what do you know about Einstein as a person, to what is the theory of relativity about, in as vague or precise terms as you like. Okay? Yeah.
Single space or double space?
Always single space. Okay. Always single space. So let me. We do it in words. 500 to 1,000 words. Okay. So single space page is 500 words. Whatever, special or general. If you know the difference, fine. If not, also fine. Okay? So that's it. I will end a little early today because I don't want to throw too much stuff at you all at once. I'll see everybody on Wednesday.
It's alright if we email this to you, right?
What's that?
It's alright if we email this to you, right?
Yes, you can email it to me.
And do I need like this?
Yes. I have syllabus and the reading list. Okay, can I get your last name just so I can check the rest? Yes. Yep. You mean the handbook?
Yeah.
What did
Is it emailable?
It's emailable. I can email you like the most recent PDF version.
And that's where you like work out your classes and
That's part. I mean, it's like a 50-page thing, but that's in. I mean, if you want, I can just print you off the checklist.
Yeah, I don't know.
that would be great.
Yeah, I can. Do you have time to run over to the lab real quick?
Oh, and what's the bookstore?
It's on here. It's called Blue Stockings. It's on the address is on here. It's on it's on the Lower East Side. Allen Street, 172 Allen Street. First page.
You can't put it in any other one? Oh, okay, great.